Welcome learners to this lecture. In this lecture we are going to understand what is the definition of residues and how to find out the residues at their pools. If Z equal to Z0 is an isolated singular point of f of Z, we can find the Lorentz series of f of Z about Z equal to Z0 as f of Z equal to sum of n equal to 0 to infinity a n z minus Z0 power n plus sum of n equal to 1 to infinity bn by z minus z0 the whole power n. The coefficient of 1 by z minus z0, that is, when n equal to 1 here in the principal part, is called residue of f of z at z equal to z0. Therefore, coefficient of b1 when n equal to 1, we are going to get residue of f of z at z equal to z0. What is this? This equal to 1 by z minus z0. From the definition of Bn given in the theorem of Lorentz series, we know that Bn equal to 1 by 2 pi I. This I should come in the denominator. 1 by 2 pi I integral over C f of z by z minus z0 whole power 1 minus n into dz. By putting n equal to 1 here, you will get the power of z minus z0 is 0. Any finite value power 0 is 1. So that's why we are getting 1 by 2 pi I integral over C f of z into dz. From this we can able to say that integral over C f of z into dz equal to 2 pi I into P1. So here the contour is defined over the Lorentz series. Lorentz series, we know that it is defined in annular region. The function is defined in annular region. So here the residue of f of z at z equal to z0 may be denoted as residue of f of z at z0. This is the representation for residue. Now if they are asking you to find out the residue, we have to find the coefficient of 1 by z minus z0 in Lorentz series. How to evaluate residues of f of z? Residue of f of z at the simple pole is at z equal to z0 is given by r equal to residue of z equal to z0 is limit z tends to z0 z minus z0 into f of z. This is the z minus z0 into f of z. If you are having residue of f of z at its pole z equal to z0 of order n is given by limit z tends to z0 1 by n minus 1 factorial, where n is the order of the pole, d power n minus 1 by dz power n minus 1 z minus z0 power n into f of z. That is, if you are having pole of order n, z equal to z0 is a pole of order n, you have to differentiate this z minus z0 power n into f of z n minus 1 times with respect to z and multiply it by 1 by n minus 1 factorial. After that, substitute z tends to z0 in the resultant. Third case, if you are having the function f of z as p of z by q of z form and the pole is a simple pole at z equal to a is given by p of a by q dash of a. P of a by q dash, that is derivative of a, q dash of a, derivative of q at the point z equal to a. Now take down this problem. Find the residue of f of z at its poles. Here the function f of z is z by z minus 1 into z plus 2. If you want to find out the pole, you have to know what is the singular point. So by equating the denominator to 0, you will get the singular points z equal to 1 and z equal to minus 2. Since the power of z minus 1 is 1 and the power of z plus 2 is 1, you are having z equal to 1 is a pole of order 1 and z equal to minus 2 is also a pole of order 1, or they are called as simple poles. So you have to find out the residue at its poles. Therefore, we have to find the residue of f of z at z equal to 1, which is a simple pole. Therefore, the formula is limit z tends to z0, z minus z0 into f of z. So by making use of that formula, limit z tends to 1, z minus 1 into z by z minus 1 into z plus 3. Now by cancelling z minus 1 and z minus 1, here you will get z by z plus 2, then put z equal to 1 here, you will get the answer as 1 by 3. Likewise, we have to find out the residue of f of z at z equal to minus 2. This is also a simple pole. Therefore, limit z tends to minus 2, z plus 2, z minus of minus 2 will give you z plus 2 into z by z minus 1 into z plus 2. Now this z plus 2 and z plus 2 gets cancelled. After apply z tends to minus 2, otherwise you won't get this answer. You will get confusion. You will get the answer as infinity. So after cancelling the common terms, then only you have to put z equal to minus 2 here. So you will get minus 2 by minus 3, which is gives you 2 by 3. Now we'll move on to the next problem. Find the residue of f of z e power 2z divided by z plus 1 the whole square at its poles. So to get the poles, we have to find out the singular points. Equate the denominator to 0. Here having z plus 1 the whole square equal to 0 gives you z equal to minus 1. It is a double pole of f of z. Why? Because you are having the power as 2 and z equal to minus 1 repeated 2 times. So that is why it is called double pole or pole of order 2. Now what is the formula you are going to apply for finding the pole of order 2 formula? Is limit z tends to z0 1 by n minus 1 factorial d power n minus 1 by dz power n minus 1 z minus z0 power n into f of z. So by applying that formula, here you are going to have residue of f of z at z equal to minus 1 is limit z tends to minus 1, 1 by n equal to 2 here, okay, here n equal to 2. So 1 by 2 minus 1 factorial d power 2 minus 1 divided by dz power 2 minus 1 into e power 2z divided by z plus 1 the whole square. That reduces to here z plus 1 the whole square, z plus 1 the whole square, you can cancel it off. You will get limit z tends to minus 1 d by dz of e power 2z. We know what is the differentiation of e power 2z one time. You have to bring this 2 to the multiplication, like 2 into e power 2z. Apply z tends to minus 1 now. You will get 2 into e power minus 2, which is the answer for this residue of given function at the pole z equal to minus 1. Hope you understood. Next, we'll move on to the next problem. Find the residue of f of z equal to 1 plus z divided by z into cos z plus sin z at z equal to 0. Here, Finding of pole is itself tricky. For finding the pole, we are going to use the power series formula. We know that cos z power series is 1 minus z square by 2 factorial in plus z power 4 by 4 factorial etc. multiplied by z will give you z minus z cube by 2 factorial plus z power 5 by 4 factorial etc. Also we know what is sin z. Sin z is z minus z cube by 3 factorial plus z power 5 by 5 factorial etc. Now by adding these two, you will get z into cos z plus sin z equal to 2z minus z cube, you can take it common. 1 by 3 factorial is 1 by 6 and 1 by 2 factorial is 2 itself. Then z power 5 is common, you can take it outside. Into 1 by 5 factorial is 1 by 120 plus 1 by 4 factorial is 1 by 24 etc. Now take z common and do the simplification. You will get 2 minus 2 by 3 z square plus z power 5 by 20 etc. So don't worry about the expansion of this. By equating this term to 0 to get the singular point, we'll get z into some expansion equal to 0. This shows that z equal to 0 or this expansion equal to 0. Definitely from this we won't get the point z equal to 0. Therefore, by equating this z equal to 0, you will get z equal to 0 is a simple pole of f of z. And here, the function f of z, we can write it like p of z by q of z form, rational form. We know what is the formula for finding the residue of f of z. If f of z is of rational form and z equal to a is a simple pole, the formula is just put z equal to a in the numerator and find out the derivative of denominator with respect to z, then put z equal to a there. So by making use of that definition, here you will get p of z by q of z at z equal to 0 gives you p of 0 by q dash of 0. Call this as equation 1. Now what is p of z? 1 plus e power z. What is q of z? Z into cos z plus sin z. So what is q dash of z? Cos z. Here you have to use product rule. Differentiation of z is 1 into cos z plus z into differentiation of cos z is minus sin z plus sin z differentiation is cos z. So you are getting 2 cos z minus z into sin z. Now at z equal to 0, put z equal to 0 in p of z. You are getting 1 plus e power 0 is 1. So 1 plus 1 equal to 2. And put z equal to 0 in q dash of z. You will get cos 0 is 1, sin 0 is 0. So q dash of 0 equal to 2. Therefore, substituting in equation 1, you will get residue of f of z at z equal to 0 is 2 by 2, which is equal to 1. Hence, we have seen all the three types of problems by finding the residue of the given function. Hope you understood. Thank you.